Right, so try out example one. Here we go. We've got ourselves a car going along the road. They give us a speed v equals 2s, where s is the position in meters per second. And we've got a constant rho, constant radius here of this curve of 50 meters. And like we said, that's a pretty good way to handle it. We could come in straight, and then we could make this road have a constant radius, easier for the drivers to be, just at one angle for a while instead of constantly, which way is this road going, right? So pretty typical road design there. We've got 50 meters. And so let's find the total acceleration. So we're going to find the magnitudes of the car's acceleration at s equals 10 meters. Okay, so we're going around a curve, so we are going to have a normal acceleration inwards to the middle in the normal direction. And also we have do we have a tangential acceleration? That's what we got to ask. If v is a function of s, that sounds to me like the velocity is going to change the more we drive. So yeah, we're changing our velocity. We also have a tangential acceleration. So let's find the velocity. We'll need that for v squared divided by rho for our normal acceleration. And we'll need to do some derivation to find the tangential component. So the velocity equation, v equals 2s, then we could plug in s is 10 meters. That's what they wanted us to find it at. So when s equals 10 meters, 2 times s would give us v of 20 meters per second. So that's just our velocity at that instant. The acceleration vector, we've got to take a derivative of the tangential component and v squared over rho for the normal component. So the tangential, dv dt, well, if we do dv dt, then we're going to end up with a chain rule. And so what they're doing here is they're saying, okay, well, what if I did dv ds, because this is in terms of s, and then multiply that by dv dt, right? We're going to do we want to do ds dt, and we'll multiply both sides by dv ds. So what happens is we end up canceling ds's, we get dv dt and dv ds on that side. So dv dt is just at, that's what we're looking for. dv ds ends up like this. So we've got v times dv ds since we multiplied both sides by dv ds. And that will simplify to just a 2 when we do dds of v, which was just 2s. So this is in terms of s. That just becomes 2 times v. So we've got 2v is at there. So we're just doing the time derivative of the v equation, right? This would be easier if the v equation was in terms of t, but we had to get a little creative because it was in terms of s, and now we've got 2v. So we just solved for v was 20 meters per second, so we could plug that in, and now we've got at equals 40, and I know that seems painfully unit-wise. We plug in meters per second and we get meters per second squared. This is another one of those things where this equation, v equals 2s, if you plug in meters there, you're also not going to get meters per second. So their equation is an equation that is not unit homogeneous, right? It's not popping out correct units to start with. So this is probably some observed data-driven equation, right? Where they're saying, okay, every time we record this data, we're noticing that there's a relationship between S and V rather than T and V. And so they just made this empirically derived formula, and that's why it doesn't exactly pop out the right units. So we just have to trust that you plug in meters here, it gives you velocity in meters per second. You plug in meters per second here, and it pops out acceleration in meters per second squared. The normal component then, we've got the tangential taken care of. Normal is v squared over rho. So at 10 meters, we knew velocity, 20, plug that in, squared divided by constant radius of rho, and that gets us 8 meters per second squared. And the last thing to do is combine those accelerations to come up with the total magnitude of the acceleration, 40.8. And that's it for that one. In the future, we could use that to continue and say, okay, well, then what is the force that we would need in our tires, friction, to not slide off the road? And we could use the normal acceleration for that, for example.